Hello everyone. So, we will start today the first lecture on the course testing of functional and technical textiles. In the first segment, as I have mentioned earlier, that we will discuss the functional textiles, that is the clothing used for functional aspects. First we will deal with the low stress mechanical characteristics. Basically, by low stress mechanical characteristics we mean that the fabric or clothing when we wear, how it interacts with our body as far as fabric handle is concerned. A clothing may be very good as far as the transmission characteristics is concerned, like moisture transmission, thermal transmission or air transmission, but if the fabric handle is not proper, then it will not be able to perform its function. So, that will be totally uncomfortable. So, the measurement or testing of low stress mechanical characteristics is extremely important. So, fabric handle, it is for industrial fabrics, the performance characteristics are very important, like for filter fabric it is a filtration characteristics, for composite there are many other characteristics, their performance characteristics are important, like geotextile its strength and other characteristics important, but for functional textiles handle is extremely important, whether the fabric is smooth or rough, stiff or limp, or its draping quality. So, or frictional characteristics, its surface roughness, its shear characteristics, okay. All these characteristics are extremely important. So, in this segment we will discuss all these low stress mechanical characteristics. So, first let us see the standard method of measurement of one of the most important low stress mechanical characteristics is the bending. So, the method which we use to measure the bending characteristics, it is called cantilever principle. So, the common method is Shirley stiffness tester, where we test the horizontal strip of fabric is allowed to bend like a cantilever under its own weight. Like suppose this is a fabric sample and in a horizontal platform if we hang under its own weight, this fabric will bend. So, from this bending angle or from the overhanging length we can calculate the flexural rigidity of the fabric. So, this is the principle where the fabric, this is a green color, it is a fabric sample and this is the platform, and when we push the fabric it bends, it is a tip point, it is making an angle with the horizontal, it is a certain specific angle, and from there we can calculate the bending characteristics of fabric. So, let us see the animation of this principle. Now, when the fabric is pushed and it is hanging like cantilever, and gradually as the length is increasing, overhanging length is increasing, its tip point, it is making certain angle. Okay. As soon as it is making a predetermined angle which is typically 41.5 degree. So, that based on that angle we can calculate different parameters, where G equal to G is the flexural rigidity of the fabric, M is the mass per unit area, L is the overhanging length of the fabric, and with this equation G equal to M multiplied by L q multiplied by cos theta by 2 by 8 tan theta, where theta is the angle with the which the tip point of the fabric is making angle with the horizontal plane, and C is the bending length which is equal to L is the overhanging length and multiplied by cos theta by 2 divided by 8 tan theta to the power 1 by 3. So, from there we can calculate the both the flexural rigidity and the bending length. Okay. So, if we know all these characteristics, so this will actually reflect the bending characteristics of fabric. This formula these are the Peirce empirical equation. Okay. From there, as I have already explained, where M is the mass per unit area and G is the flexural rigidity in micronewton meter and C is the bending length in millimeter. Okay. From there we can calculate these two G and C, these two parameter, it shows the fabric bending characteristics. And if we know this empirical formula, from there we can calculate for theta equal to 7.1 degree, this total parameter, this the right hand side parameter, it becomes 1, okay, which means that the overhanging length is equal to the bending length for theta equal to 7.1 degree. So, that means the higher the bending length, the stiffer will be the fabric. So, we can get the value directly from the overhanging length. The main problem is that we can have in our instrument the angle 7.1 degree. In that case, directly overhanging length will show the bending length, but the problem is that the fabric, as the fabric is very flexible. So, measurement of 7.1 degree, that it will come immediately after that, after the hanging. Okay. So, that is why we normally do not use the value 7.1 degree. So, we can define the bending length C in this way, that the length of a rectangular strip of material which will bend under its own mass to an angle of 7.1 degree. That means, the overhanging length L which will make 7.1 degree with the horizontal plane, that will be equal to the bending length. So, in Charley stiffness tester it works in the same principle. So, where we use the specimen, the width of the specimen. So, this is suppose a specimen, it is a 25 millimeter, approximately 1 inch, and it is a 200 millimeter, it is approximately 8 inch. Okay. So, that is the specimen dimension. So, it allowing this strip to bend to a fixed angle 41.5 degree under its own weight. So, why is it 41.5 degree? I will just come. So, the overhanging length L is twice the bending length C. That means, to make the equation simple, it will be twice than that of the bending length. So, bending length will be exactly half to that of overhanging length. To make the equation simple, so we may keep it 41.5 degree. So, that means, if the theta becomes 41.5 degree, then this total value, this function of theta will become 0.5. So, we can get directly C equal to L by 2. So, to have this simple equation, we have to keep this angle, that is 41.5 degree. So, from there we can get the flexural rigidity, which is m L q multiplied by cos theta by 2 by 8 tan theta. So, it is the ratio of small change in bending moment per unit width of the material to the corresponding small change in curvature, that is the definition. Okay. And we can calculate this G flexural rigidity in terms of micronewton meter with this formula, m multiplied by Cq multiplied by 9.807 multiplied 10 to the power minus 6, where m equal to mass per unit area in gram per square meter, C is the bending length in millimeter, and bending modulus, it is the stiffness of a fabric in bending is dependent on its thickness. That means, for similar structure, if we increase the thickness, the stiffness will increase. Okay. So, if the flexural rigidity is same, still we can have different bending stiffness if we increase the thickness. That is why the thicker the fabric, the stiffer it is. So, if all other factors remain constant, so that means we have to have certain equation, certain parameter which will be independent of thickness, that is the bending modulus is independent of the dimension of the strip tested. Okay. So, that means it should be independent. So, that by analogy of the solid material, it is a measure of intrinsic stiffness. Okay. And this intrinsic stiffness or bending modulus can be expressed in terms of 12 multiplied by G multiplied by 10 to the power 3 divided by T q, where T is the fabric thickness. So, we can actually divide by T q to get the bending modulus. Now, let us try a couple of numerical to understand the how to achieve the overhanging length from different parameters, known parameter. So, here the problem is a fabric with certain mass per unit area, that is 200 gram per square meter mass per unit area, having flexural rigidity of 245 micronewton meter, that is the flexural rigidity. What will be the overhanging length? If the tip of the specimen has to reach a plane inclined at 10 degree below the horizontal. So, that means the fabric, suppose this is the fabric of mass 200 gram per square meter and it has got flexural rigidity of 245 micronewton meter. Now, the question is that what will be the overhanging length we have to calculate when this tip will reach a point which is 10 degree below the horizontal point. So, that is the question. Now, the solution, if we see the data which are given here, so fabric mass per unit area is given 200 gram per square meter, flexural rigidity is given, G is equal to 245 micronewton meter, theta is given 10 degree, and we have to calculate the overhanging length. So, we know this formula G equal to m c q multiplied by 9.807 multiplied by 10 to the power minus 6 micronewton meter. Okay. That is the flexural rigidity is known here. So, m is mass per unit area in gram per square meter and c is the bending length. So, first we have to calculate the, we know the bending length. So, this is the bending length is c here. So, we can calculate the bending length from all the given data, and here bending length comes out to be 50 millimeter. Okay. From this data, so bending length we have calculated, and from there this is the formula by given by Peirce formula as we have discussed earlier, and using the data here c is known, theta is known, theta is here is 10 degree. Okay. So, from there, so bending length c equal to L and function of theta, this is the function of theta. So, from there we can calculate that function of theta is cos theta by 2 by 8 tan theta power 1/3. So, theta is 10 degree. So, cos 5 degree by 8 tan 10 degree by 1/3. From there we have calculated function of theta is 0.89. So, C from there we can calculate the overhanging length. If we know the value of C 50 millimeter, 50 by 0.89. So, it is coming out to be 56.18 millimeter. So, which means that we have to have 56.18 millimeter overhanging length to have 10 degree when the tip of the fabric will reach 10 degree below the horizontal plane. Similar problem, another problem which is exactly similar to that, a fabric with mass per unit area of 250 gram per square meter has flexural rigidity of 275 micronewton meter. What will be the overhanging length? Exactly same. If the tip of the specimen has to reach a plane inclined at 14.2 degree below the horizontal plane. So, the treatment will be exactly same as earlier. So, here we have to get the theta value is known. So, we have to get the overhanging length. So, G is this is the formula which is given. So, from here from the given data we can calculate the bending length which is 48.22 millimeter and C equal to L function of theta. So, we can calculate the function of theta if we know the angle. So, here angle is 14.2 degree. So, 14.2 degree using theta equal to 14.2 degree, we have got function of theta is 0.79. So, using this value we have got the value of overhanging length 61.04 millimeter. So, this 61.04 millimeter. So, we can calculate any data, anything if we know the basic equations. So, after the basic bending, so this is the isolated instrument. So, there are different instruments which we can measure the low stress mechanical characteristics. Even we can use the some simple tensile tester to measure the low stress mechanical characteristics, but one few complete instruments are available. So, one of them is the Kawabata evaluation system. Okay. Now, the question is at what condition the bending length C is equal to the overhanging length. The condition is simple, the function of theta, this part cos theta by 2 by 8 tan theta to the power 1/3. If we have something for certain value of theta, if it is say 1, then the C equal to L, then we will get C equal to L. So, for theta equal to 7.1 degree, so we will get this value. So, C equal to L we can achieve at the value of theta equal to 7.1. So, this is the value, and for theta equal to 41.5 degree we get function of theta equal to 0.5. So, ideally that function of theta should have been 1, then we can directly use the value overhanging length equal to C. As I have mentioned, as the fabric, most of the fabric samples are stiffer in nature. So, we cannot get the it is and 7.1 degree is very small angle. So, it is very difficult to measure the value exactly correctly. So, we use the next value, easy value, simple value, and where function of theta is used of 0.5. So, that we normally use, and in most of the instruments like your Surley tester or fast test bending tester, we use the value 41.5 degree. So, this is the simple formula. If we get the overhanging length, then half of that is the value which is the bending length. So, that is why if we see carefully the scale in Surley tester, it is 1 centimeter which is showing, it is typically it is a actually it is a 2 centimeter. It is gauged in such a fashion, so that directly we get the value, the overhanging, it is not the exact overhanging length we are getting, it is the bending length. So, that is why the scale there is just doubled. Okay. It is used in Surley stiffness tester. Now, so the bending by cantilever method we can use for fabrics which are little bit stiffer in nature, but for fabric which are very limpy like knitted fabric, weft knitted fabric, these are very flexible. In those fabrics we cannot use the cantilever principle. For those fabrics we have to use another method which is hanging loop method. So, hanging loop method for very limpy fabrics do not give satisfactory results in cantilever principle, like loose knitted fabrics as I have mentioned. The stiffness is measured by forming them into a loop and allow it to hang under its own weight. Like this is a fabric, suppose it is a very limpy fabric. So, what we have to do? We have to form a loop. So, this is a loop formation. Now, without any deformation, suppose it is a circular loop. Now, when it is allowed to deform under its own weight, this will form little bit, it will be deformed. So, we have to measure the degree of deformation. From there we can calculate using different equations, we can calculate the bending characteristics of fabrics. So, L is the length of the strip, okay. L0 is undistorted length of loop, that is the distance between the grip to the farthest point. After hanging, due to their own weight, the distance become L, and the deformation, that is the difference between the L and L 0, which is used to calculate the stiffness. Now, let us see, basically there are 3 types of loops available. This is fabric, which is very limpy fabric. Now, we have 3 different types of loops. One is, suppose we are making a loop form, this fabric has formed in the form of loop. This is ring loop, okay, where undistorted length, this length is L 0, and when and at this is the joining point, and when it is hanging on its own weight, this will be deformed little bit. So, this length from the point of grip to the farthest point, this is L. So, the distance, the difference between L and L 0, it is a deformation. Okay. So, using this value D, we can calculate the stiffness of the fabric. This is the formation, it is called ring loop. Another formation which is we can form, suppose this is the fabric, and if we have this type of formation, it is called ring loop, which is 1. Second formation, this is the fabric which is formed in this fashion, just like pier, it is a called pier loop. So, without deformation, this is pier loop L 0, and on its own mass, if it gets deformed, L. So, D equal to L minus L 0. Similarly, third type of loop, which is called heart loop, it forms like heart, heart shape. This is the heart loop. Now, here the strip we are forming just like heart, and we are gripping here. From here the length is L 0, and when it is deformed on its own mass, L. So, D equal to L minus L 0. So, which means the stiffer the fabric, the deformation will be lesser. So, D will be lower, for stiffer fabric D will be, the D value will be lower. So, depending on the D value, we can calculate the stiffness of the fabric. So, D is the difference between L and L 0. So, the ring loop method, this is the gripping point, and after deformation the length is L. So, L 0, as it is a ring, it is a circular one. So, L is the total length, which is circumference. So, that divided by pi, it is a very simple. From there we can calculate the L 0 equal to 0.3183 L. So, if we know L 0, and then we have to calculate the L value. So, L value if we calculate, and from there the bending length is given by this formula, L equal to C equal to L multiplied by 0.133 multiplied by function of theta. So, function of theta is given by this formula, and this function of theta is same for all the other different types of loop method, hanging loop method, and theta here is given by 157 degree multiplied by d by L 0. So, d means here the difference. Okay. If we can calculate this difference, so we will get different value of theta, and from there we can calculate the function of theta, and using this function of theta value we can get the bending length, okay, and knowing the length of the strip. Okay. This is the, and for other loop method only difference will be this two formula, this formula. Okay. Now, for pure loop method, L 0 is equal to 0.4243 L, C equal to L multiplied by 0.133 multiplied by function of theta divided by cos 0.87 theta. Okay. This is the difference in equation, and theta again it is 504.5 degree multiplied by d by L 0, where function of theta remains same. Okay. Similarly, in Hart loop method, as I have already shown, so this is the L length after deflection, this is a small l, it is not the actually it is a small L length. Okay. And here this L, capital L is the length of the total strip. Okay. From there L 0 equal to 0.1337 L, it is the length of the strip, and this one is a smaller length. So, C equal to L multiplied by 0.1337 multiplied by function of theta is given here, and theta we can calculate, which is again function of deflection. Okay. So, from there, and L 0 is a constant for a particular type of loop. For Hart loop, this is the constant value, only d value is a function of the stiffness. So, stiffer the fabric, the d value will be low, and that changes the theta value, and theta value changes the function of theta value, and from there we can calculate. So, this is the process we can calculate, and this method is used, this method basically we can use for very flexible fabric, which where we cannot use the Shirley stiffness tester. This is the point where it is a gripping point. Now, we will start the low stress mechanical characteristics measurement. So, there are mainly two commercially successful instrumental approaches. Why it is called instrumental approaches? Because it is not the single instrument, this is a set of instrument, and we get the data from each and individual instrument and use for evaluation or interpretation. Okay. So, these two commercially successful instrumental approaches to measure the low stress mechanical and surface characteristics of fabrics, which are actually used to measure, to assess the handle characteristics of functional textiles. These methods are the Kawabata evaluation system KES and the fabric assurance by simple testing. In short, it is called FAST. KES and FAST methods are used to measure the low stress mechanical characteristics of fabrics. So, all these low stress mechanical characteristics earlier used to measure by subjective testing, but these objective methods actually there are correlation between subjective assessment and corresponding mechanical measurable fabric properties. These are the subjective assessments like smoothness, firmness, fullness, crispness, hardness. This we can actually assess subjectively. This we cannot measure directly by objective method, but they are correlated with the objective assessment by low stress mechanical properties. These low stress mechanical properties are tensile and shear characteristics, very low stress tensile characteristics. We are not talking about here the stress up to the end point, breaking point. Here we are talking about the very low stress, which is actually used for fabric handle characteristics, and shear, then low stress bending characteristics, low stress compression characteristics, and surface frictional characteristics or surface roughness characteristics. If we combine all or some of the characteristics, this objective assessment values, we can predict the subjective assessment values like crispness, fullness. They are directly related with all these low stress mechanical characteristics. We will discuss in detail, and this Kawabata evaluation system, it has got 4 modules. In module 1, KESF 1, which is used for measurement of tensile and shear characteristics. KESF 2 is used for measurement of bending characteristics. So, where the bending means it is not at very high level, it is at the low stress, at lower extent of bending. Similarly, in KESF 1, the tensile characteristics is it is at a very low level of stress. Okay. Similarly, for shear characteristics, KESF 3, it is for measurement of compressional characteristics, okay, and KESF 4 for measurement of surface friction and roughness characteristics. Now, the speciality of KESF methods are, here we measure both in loading direction and also in the unloading direction, be it tensile, shear, bending, compressional, even for the frictional characteristics. We can get the data for each and individual point, and accordingly we can analyze. So, if it is tensile characteristics, it will stretch the fabric, we will measure all the data during elongation, and also during unloading we will get all the data. Okay. Whereas, the fast systems, these are much simpler. So, and it has been developed by CSIRO Australia, and primarily for control and assurance of fabric quality, okay. And it also gives the objective indication of fabric handle characteristics. Now, the difference between fast system and the Kawabata system, in fast we do not get the value or data in between during the extension or during compression, we get only value at end point, okay, and it is a discrete data we get and we analyze the data. Whereas, in KESF method we get data, the overall data, total curve we get. Okay. The fast method, it consists of a series of 3 instruments and one test method. Okay. The instruments are the first one which measure the compression, it is called compression meter. First 2 measures the bending characteristics bending meter, it is similar to that of Shirley stiffness tester, and first 3 it is a extension meter. In addition to all these 3, we have a test method which is called first 4, which is not an instrument, it is a just a test method, where we measure the dimensional stability, okay, and it's a these methods are basically it is inexpensive, and this is only a guidelines, okay, from where we can measure the dimensional stability, hygral expansion, okay, and relaxation of shrinkage we can measure. So, first we will start with the Kawabata evaluation system of fabric, KESF system. So, we will start with the first module, which is KESF 1, which measures the 2 characteristics, okay, tensile characteristics and shear characteristics. The fabric specimen is clamped between 2 jaws. Okay. So, for any tensile characteristics we need 2 jaws. Okay. Here similarly, we have to have 2 jaws for clamping the fabric. One jaw is attached with the drum for measurement of tensile force. So, there will be one jaw, the drum will rotate, as the drum rotates it will apply the force. A constant tension of 10 gram force per centimeter is applied by weighing the which is attached to the drum. So, a constant weight is hung on that, and then it is gripped, and other jaw is attached with the slide for shear force application. So, one jaw is a slide, another jaw is a drum. Okay. So, this is the picture, and here this is the rotating drum, and this one is fabric specimen, okay. And one jaw, this is jaw which is attached with the drum. As the drum rotates, this will extend the fabric, stretch the fabric, and the load will be applied on the fabric specimen, and other jaw which is connected with the this slide, this is shear for measurement of shear. So, this slide is is the other jaw. That means, when the instrument works in tensile principle, tensile force principle, in that case this slide, this other jaw will be stationary, only this drum will rotate. So, as the drum rotates, this will apply the tensile force on that, on the specimen, and the elongation we can measure by the tensile strain detector. Here strain detector, this strain detector works on this measures the angle of rotation. So, this angle of from this angle of rotation, if we know the diameter of the drum, we can convert it to the how much extension is applied, and this tensile force detector, which is nothing but a torque sensor. So, the torque required to rotate this drum is actually is converted to the form, that is the tensile load. Okay. So, from these two sensors, one is tensile strain detector and tensile force detector, we can get the value of the stress strain. We can completely get the stress strain curve, and after rotating, after straining predetermined length, this drum will automatically start rotating in other direction and it will record the value for the load and extension during the unloading time. Similarly, once this instrument works on sliding mode, that is to measure the shear, in that case the drum will be stationary. So, one should remember in this instrument, although we measure both tensile and shear, but they are not simultaneous. Once the tensile measurement is over, then the drum will be stationary, then the slider other jaw will start moving, it will start moving laterally in left to right direction and again it will come back from right to left direction. Here again we have two sensors, one is that the shear strain sensor, again by the rotational angle, from the rotational angle, and if we know the gear ratio, we can calculate the shear strain, how much shear it is taking place, and the shear force detector here, it's again it's nothing but again torque sensor, it's a torque required to slide this slider, it's calculated, from there we can get the shear stress and shear strain value. Now, let us see the animation here. Here this is the fabric sample, fabric specimen, the drum is there and it is a fabric is clamped on the drum and another is on the this slider, and here it is a tensile strain detector which will detect the rotation of the drum, and here is the tensile force detector which is nothing but a torque sensor, and here is the shear strain detector and shear stress detector. Okay. Now, we will start here the animation. First we will start with the tensile mode. Okay. Now, we have started. Now, this drum is rotating in clockwise direction. So, fabric is getting stressed, extension is taking place and it is a plotting, elongation is there. After reaching the predetermined mass, predetermined force, that is 500 gram force per centimeter, it is coming back again. So, it completes one cycle and from there we can calculate various parameters, just we will discuss here. The parameters here we can get 3 parameters here from this loading and unloading curve. Okay. Stress strain curve, this is the elongation and here is the force elongation curve. Here we will get the first parameter, it is a Wt, which is tensile energy, that means the tensile energy during the loading curve. Okay. So, it is the area under the loading curve, the energy required to load stress the fabric, which is expressed in terms of Wt. Next is the linearity, LT, linearity of the curve, which is nothing but Wt, that energy required for extension, and if the curve was straight line, that means it will form a triangle, the area of this triangle, that means linearity of the curve, it is a Wt by area of the triangle AOB, this AOB triangle. That means, if the curve is linear, then the value of the LT linearity would have been 1, and as WT is less than the area of this triangle, that means this value will be LT value will be less than 1. So, from there we can actually get idea about the linearity of the curve. Similarly, resilience RT, resilience during stretching, which is nothing but the area under the recovery curve, that is R recovery curve divided by the area under the loading curve, which is equal to multiplied by 100. So, resilience, if the resilience is 100%, that means the recovery curve will follow exactly to that of the loading curve. If they are actually coinciding, that means the fabric will be highly resilient. So, from these two values, that is area under the recovery curve and area under the loading curve, we can get idea of the resilience. Resilience characteristics is that characteristics where it actually return, it comes back from the a deformation. It can be a tensile resilience, it can be compressional resilience, it can be of any form of deformation. So, we need a fabric with very high resilience. Okay. So, that is why resilience characteristics we can get from the area under the loading curve and area under the recovery curve. Now, this instrument, now we will see what will happen when it works on the shear mode. Now, once it is moving on shear mode, this drum will be stationary. Now, this slider will move from right to left and left to right, okay, and we will get the shear curve. Okay. Here we are getting the shear strain and shear stress curve. So, from this shear curve, because it is not following the same path when during shear and during again when it is repeating, it is not following the same path while shearing and when it is coming back. This is basically due to the hysteresis. This phenomena is known as the hysteresis, which is basically it is a characteristics of textile material due to the frictional characteristics of frictional force, which is restricting the shear. So, shear stiffness, which is nothing but slope of curve between 0 to 2.5 degree. So, this curve, if we take the slope between 0 degree shear to 2.5 degree shear, so that will give us the value of the shear stiffness G. Another parameter which is 2Hg, which is nothing but the hysteresis of shear force at 0.5 degree shear angle. So, if we take the shear angle here, we have maximum 5 degree shear angle, it is here. So, we can get the shear angle here at 0.5 degree shear angle. If we take the hysteresis, this will be 2 Hg, and if we take the shear hysteresis at 5 degree shear angle, that is the 2 Hg 5. So, here in shear mode we get 3 parameters. So, that means in KESF 1 module we get total 6 parameters, 3 parameters for tensile mode and 3 parameters for shear mode. Okay. Now, let us see the test parameters. Now, as I have already mentioned, the parameters measured is tensile force, which is indirectly measured through the torque required to rotate the drum, tensile strain, angle by angle of rotation of the drum, shear force is by a transducer, which is force required to slide the slider, and shear strain which is nothing but by displacement of the slide, and this working principle we have already explained, discussed here. Now, parameters for measurement of tensile characteristics are the loading conditions, and parameters are here. The setting and loading conditions are rate of extension. Here the rotational speed of the drum is actually maintained in such a fashion, the rate of extension is actually 0.1 millimeter per second, and sample size is length multiplied by width, is length here is a smaller. We should remember, suppose if it is the sample size, this will be the length and the width will be 20 centimeter. That is why this is the grip, and in this way it is stressed, and maximum tensile force is 5 Newton per centimeter. So, these are the loading condition. So, the drum will come back, will start rotating in the other direction once it is reaching 5 Newton per centimeter, that much force. The characteristics which are measured, so parameters measured for tensile characteristics are KESF 1, which is test parameters and units are elongation at 5 Newton per centimeter tension, which is EM, is expressed in percentage. So, elongation EM means at 5 Newton per centimeter, that is the elongation percentage. Energy in Newton meter is required to extend the fabric specimen up to 5 Newton per centimeter tension, which is WT, it is energy, that is the area under the loading curve. Linearity of stress strain curve LT, which is unitless, I have already explained. Tensile resilience RT, which is expressed in terms of percentage, which is the ratio of the energy required for recovery curve and the loading curve, which is the tensile characteristics. These are the tensile related characteristics, and the shear related characteristics. For that, setting and loading conditions are, the speed of shearing is 0.417 millimeter per second, that is the sliding speed. Sample size remains same because we use the same sample size. Maximum shear angle is plus minus 8 degree, which is equal to 140 milliradian, and constant sample tension is 0.1 Newton per centimeter. These are the setting and loading conditions, and the loading condition and parameters measured are the shear rigidity is nothing but at 2.25 degree. Okay. So, it is at 2.25 degrees shear strain is expressed in terms of Newton per meter, which is nothing but 39.4 milliradian. Shear hysteresis is at 0.5 degree, that is 2 Hg, and shear hysteresis is at 5 degree shear strain, which is 2 Hg 5, is expressed in terms of Newton per meter. Okay. So, these are the parameters related to KESF 1 for the shear characteristics, and for working principle of KESF 2 we will discuss in the next class. Till then, thank you for listening.